Thanks for the introduction and for the chance to talk here. I guess I can start out by pointing out there was a small transcription error in that introduction. I'm not trying to enable the arms race. I'm trying to end the arms race. So I guess in terms of keeping myself in work, it might be good to enable it. I don't know. So I'm going to be talking about some, at one level, old ideas from computing, how we can mathematically prove that our systems are correct, and give a sense for how these are, maybe surprisingly, a potential solution to the long-standing problem of how we make sure the systems we deploy are secure, and give some evidence that there's been recent progress with actual deployment in industry for these kind of abstruse-sounding techniques. So in security, we are used to the arms race mentality, where the good guys are constantly developing new approaches to making systems more secure, and then the bad guys find new attacks that get around the defenses, and we just iterate, and it's hard to tell where we're making progress. And there are a few reasons why this is tough for the good guys. One is that the defender in this kind of situation needs to anticipate all attacks that might lead to some compromise of a system, whereas the adversary of the defender wins if he's able to find just a single vulnerability in the system, can get in, exfiltrate data, take the system down, whatever he's trying to do. Another challenge for the defender is that it's often relatively easy to spell out what is a security policy that, if followed, would guarantee your high-level objectives. Like, we can sort of write down what's a buffer overflow, what does it mean for a piece of software not to be vulnerable to buffer overflow attacks, but then to actually deploy a system that meets this policy, we have to bring in all sorts of complicated mechanisms, which themselves are artifacts that might have bugs. And if you're not careful, you might actually decrease the security of your system by adding new security mitigations. The defender will naturally want to break a large engineering project across many pieces, probably given to different teams within an organization. Each of them has its own requirements and maybe its own security analysis. Unfortunately, thinking of the pieces separately is not enough, because the attacker doesn't have to promise, I won't look for vulnerabilities that arise only because of surprising interactions between the pieces that different teams have built. So we get this kind of combinatorial explosion of all these different connections that we need to worry about and maybe do a separate security analysis for. It is also tempting to jam a system full of as many security mitigations as we can think of, keep buying another tool this week that promises some additional security benefit, but now the user of your system faces new challenges in properly configuring all these different mitigations that have been added into the system. And human error can avoid the warranty that you've worked so hard to establish by coming up with this security strategy. Okay, so the question I want to pose to you is, how can we take a step back and rethink the way that we develop systems so we can get rid of some of that advantage that the adversary has in a security and privacy context? And the solution I'm going to be pitching is based on some early foundational work in computing in the area of formal methods. How can we mathematically prove that systems behave as they should? And I'm going to talk about a particular take on this that I'm calling end-to-end mechanized proofs of functional correctness. And I'm going to unpack the different parts of this description on the next few slides. So when I talk about mechanized proofs, what does this mean? It means you have the source code for your real system, and the engineers who built that should also write what we'll call a formal specification that says how they expect that system to act. And this specification will be source code in yet another language that you can open and edit in your favorite editor, just like your program source code. And also, crucially, the engineers are investing in building proofs, or logical arguments that show why the system meets the specification. And the proofs are code in yet another language that you can open up in your programming environment. And crucially, instead of relying on fallible humans to take a look at the proof, as they might do, say, in a submission to a math journal, these proofs are written with such a level of rigor that we can actually feed them to an algorithm that establishes whether the proof is convincing that this system meets this specification. And my lab uses a particular theorem-proving software platform called COQ. There are a number of others out there that are used increasingly in industry, but especially in academia. Okay, so we have this technology. What should we prove about our systems? I mentioned proofs of functional correctness. What does that mean? We might be tempted to take very generic properties, say a software program should not crash. That is useful to know, but I'm going to try to argue for the benefits of much stronger, more specific theorems. Something like this program actually outputs the right answer. And being completely formal about that means really knowing what this program is supposed to accomplish in the world. And finally, I'm going to argue for end-to-end proofs, which means when you have a complex system naturally split across layers, you should have a specification and a proof for each of the layers. But more importantly, beyond that, it's important to invest in composing these proofs together to get some sort of whole system result. Okay, so for instance, we can take these ideas and apply them across entire computing stacks, ranging from the hardware circuits at the bottom up through low-level software programs, high-level software programs, and application requirements in some flavor, like we're trying to implement a network protocol and it uses cryptography, and we can use classic ideas from cryptography to express what security means in this setting. We can do proofs at all these levels of a system. We can check them automatically. We can bring them together into whole system results. So this so far is closely connected to the classic vision of formal methods that folks like Dijkstra were looking at probably as early as the 1960s. But how does it pay off for these security problems, which are a relatively more recent concern? I told you about how one of the issues here is the defender needs to anticipate all attacks. The attacker only needs to find one vulnerability. A kind of magical thing happens when you do these functional correctness proofs of your system. Suddenly, if you're able to prove almost anything that is quite specific to the application, then this rules out a whole wide range of potential attacks. And here's the reason. Let's say you wrote a program that's supposed to sort a list of numbers, and you proved it. It sorts a list of numbers. Now you wonder, does this program have a buffer overflow vulnerability where the attacker could take over my whole computer by sending the wrong input to the program? Well, if the attacker could take over your computer, he could probably stop your program from sorting lists of numbers, so you probably couldn't prove that your program always sorts lists of numbers. This is the surprising payoff from proving almost any very specific functional property about a real body of source code. We no longer have to enumerate attacks. We're immune to quite a few broad categories by construction. Nonetheless, sometimes we're still surprised. About 4 years ago, there were security attacks called Meltdown and Spectre that had to do with taking advantage of surprising interactions of different parts of computer processors. And secrets in applications could be leaked through the timing of the hardware execution. I know a lot of the theorems I was proving before then definitely did not account for this problem because we weren't even thinking about the time aspect of system execution. But that doesn't mean now we have to start enumerating all the possible time-based attacks. Instead, we can just decide the theorems we prove should say things like, I have a formal model of the timing behavior of a system. I have an idea of what are the secret inputs to that system, and I'd like to prove the secret inputs have no effect on the timing of the system. Now we're ready for Meltdown, Spectre, and all the other cleverly named attacks that followed from them in this broad category. I mentioned how we had these issues where attackers can take advantage of surprising interactions across components that maybe even different teams developed. When we commit to doing end-to-end proofs that cover all the layers of a system, we force ourselves to confront all of those interface challenges. And if there was ever a place where something weird happens connecting layers, presumably when we try to do the proof of the full system by drawing on the theorems about the individual parts, we will fail to prove some important property, since it isn't even true here. And that'll force us to notice that we made some mistake in the design of the interface of one of the pieces of the system. So it's a good drive towards thoroughness of thinking. Okay, so that was all pretty abstract. Let me tell you about two specific case studies that my group has undertaken recently. And the first one of them is in the domain of cryptography. And it's targeting a small but important part of real computer systems like web browsers and web servers. So let me give the cartoon version of where our tool fits into the picture of secure web browsing. Your web browser wants to talk to a web server out there, and it wants to know it's talking to the right web server. So say you don't give your credit card information to some fly-by-night operation. And the web server has been issued a certificate by a certificate authority that says, let it be known, this web server is run by this company. And this is connected to a public and a private cryptographic key. So the browser initiates communication with the web server by going through what's called a key exchange protocol, where they establish a shared secret. So now there's some cryptographic key that we hope only these two machines in the whole world know about. But the browser still wants to check the web server was the one it thought it was. So it has to get a hold of that certificate and that public key, and then ask the server, prove that you know the private key, which it does by generating a so-called digital signature that requires the private key as an input. And then the browser can check that. And if that passes, then OK, this is a good connection. And then we can go into the main part of the communication, like sending pages and images that use this symmetric key that was established. So the first two steps of that process that are using so-called public key cryptography only need to run once per session of this protocol. But when you visit a complex web page, you're probably going through many such sessions, say downloading a whole bunch of images as separate connections. And so the performance of these first two steps is important in both the web browser and the web server that's talking to you. And balancing that performance requirement with correctness and security is a big challenge in this domain. And I was kind of interested and surprised to learn that one of the trickiest parts of this code is arithmetic. Doesn't sound so bad, right? But it's with really big integers that can't even fit in the slots that the hardware makes available for single numbers. And we're doing this modulo large prime numbers. That's important for the security properties of this cryptographic system. Still, that doesn't sound so bad. But how does this work in practice? How does the code get written for these kinds of implementations? There's a moderately large set of algorithms that are parts of different internet cryptographic standards. Then these are parameterized, most importantly, by large prime numbers. There's a moderately large set of primes that appear in different standards. And then there's a small but not trivial set of different categories of hardware that we might want to target. And you need to generate different code with different data structures and algorithms to get good performance on different categories of hardware. So the state of practice when my group started looking at this problem was that when someone picks a new selection of one dot from each of these bubbles, a selection no one had implemented before, what do? They rewrite all the code from scratch in C or assembly language, because this was viewed as the only way to get acceptable performance for this really critical kind of code. But of course, you can imagine that's an extremely labor-intensive and a bug-prone process. You could easily introduce a small issue that doesn't show up in most scenarios, but in the face of a clever attacker, all of your security and privacy is compromised. So we decided to try to automate this process in a way that gives strong mathematical assurance that different variations on algorithms in this space are implemented correctly. For instance, I'm showing you here an example of what our tool produces for one algorithm targeting 64-bit versus 32-bit computers. I hope it's clear from the font size. I'm not asking anybody to read this in detail, but the big takeaway is when you squint at this, it's not obvious it's the same algorithm on the two sides. And we can certainly be glad if we don't have to write both of these pieces of code by hand, and there are even longer and more complicated examples that show up in real cryptographic algorithms. So it's a big advantage to have a formal machine check proof that one of these generated C files gives the right answers on any inputs. So the approach that we took is to build a library that's parameterized over a choice of an algorithm variant in that space that I talked about. And given a choice, it produces fast C code, and actually code in a number of other languages these days. The library has a formal machine checkable proof. So no one has to believe that this is a correct tool. You can download it from GitHub and recheck the proof for yourself. And I don't have time to go into too much detail about what's happening inside this library, but there are a number of different stages. We start out with high-level implementations of important algorithms like multiplication, modular, inverse, other classics like that. We formally prove that each of these high-level algorithm templates is correct because they're parameterized by some of these dimensions like the big prime number. And then we have various compiler-style operations that we apply to those high-level functions to specialize them to the particular parameters that were chosen to get nice, lean, fast code out. All of those transformation processes are themselves formally proved, and all these proofs fit together into the top-level guarantee that this is a correct code generator with respect to our whiteboard-level idea of number theory. Okay, so how do we validate that this code can actually compete with the experts who are handwriting these algorithms in the past? Here's the result of one experiment we ran comparing our tool with the previous best, completely generic implementation of big integer modular arithmetic, and that's the GNU multi-precision library. And on the x-axis here, we're showing the size of the prime numbers that we use as modulus of arithmetic, and the y-axis is showing running time on a representative benchmark. And you can see here that our approach is typically doing in the neighborhood of 5 to 10 times better on running time compared to this generic solution that was out there previously. And this is targeting, say, a 64-bit laptop. We also ran an experiment targeting a 32-bit mobile phone, got pretty similar results. So we were able to pretty handily beat the performance of this generic tool that had existed on all these primes that we found on an electronic mailing list about cryptography. We wanted to try to automatically generate all the variations that were being talked about in this corner of the cryptographic community. And we do all this with strong mathematical guarantees, much better than you get with conventional software, like this library that I'm comparing to here. Also, it's really important to compare against the handwritten code by the experts. And here, we did generate the fastest known C code for all of the variations of elliptic curve cryptography, which is what we're focused on in this project. I'm just showing one example here. P256 turns out to be one of the most important cryptographic algorithm or primitives for secure web browsing. Your web browser definitely speaks this cryptographic algorithm. And so we have the fastest C code, and this is one of the harder elliptic curves for us to implement efficiently. So when we compare with handwritten assembly code, we are about a factor of 2 off. And we have some ongoing research that's closing some of that gap. But already this was a pretty compelling case for adoption, to be able to basically sleep better at night knowing that your cryptographic code is correct and secure, even if it might be a little slower than you could get by breaking out the assembly code. So we were able to, basically through students doing internships at companies, take this open source tool and push it out into the real world. So this tool is now used to produce parts of the secure web browsing code for all the popular web browsers. This is just a screenshot from the web page my student who led this work put up to summarize adoption. And adding all these numbers together, the conclusion is probably over 95% of HTTPS secure web connections these days by browsers are running our code, which was actually produced using a computer theorem proving tool, and which is able to formally certify the correctness of the code that it produces. Okay, so this is an example about a pretty small, specialized kind of code, which nonetheless really pays its way in security benefits. I also want to tell you about another case study, which is covering more of a computing stack, but maybe not doing as much in terms of application level interest in computing. But we wanted to look in the domain of Internet of Things systems, where there are increasing security and privacy concerns about what devices throughout our lives and our homes and our businesses might be able to learn about us and share with unscrupulous parties against our will. And what we decided to look at here is this system. We created a physical prototype, and we call it the Verified Internet of Things light bulb. It's kind of the simplest application you can imagine that deserves to be called a complete IoT system. Its only job is to turn a light bulb on and off based on network requests. So here's our Ethernet card, which is our bridge to the internet. And here's a power strip with a light bulb plugged into it, which conveniently can be turned on and off by wires that come out of a general purpose computer. Here is that computer. It's an FPGA onto which we've loaded our own hardware design and software stack, which we created from scratch actually inside the theorem proving environment. So we kind of have a unified IDE for writing code alongside its specification and proof. And we developed our own hardware and software programming languages, and we used them to build all the digital layers that we need for this system. And when everything is running together, network packet arrives, light bulb turns on, network packet arrives saying something else, light bulb turns off. So what do we want to make the theorem that we prove about this system? So it's concerned only with what's inside this purplish rectangle. We're considering all the code of this system together, all the digital parts describing both the hardware and the software as a unit, and we want to prove that they correctly implement our idea of what it is to turn the light bulb on and off based on network traffic. So to get a little more technical about this, we have our complete hardware-software stack as a black box. It has some wires connecting it to the world. Some of them are input, some of them are output, and they store single bits at every instant in time. We want to consider all traces the system could generate, where we're kind of running a stopwatch every period. We look, what are the ones and zeros on these wires? The input wires are containing values that the world imposes on us. These are set based on, for instance, what packets arrive over the internet. We need to be ready for any values that might pop up on those wires in any of the instances of execution. But the output wires are our responsibility to set properly based on the inputs that we've seen up to each moment. So the formal theorem about this system is an appropriate translation of this English sentence. The output pin controlling the light bulb is on exactly when the last valid packet from the internet said, turn light bulb on, and there wasn't one in between that said, turn it off. So this is a good example of a very application-specific kind of property, but I'll remind you there are really nice payoffs for general security concerns. Like we might wonder, could someone send an appropriate packet to this system, take it over, and make it join a botnet? Well, no, because being on a botnet is different from turning a light bulb on and off. And we proved this system only turns a light bulb on and off, so it's definitely not joining a botnet. And all sorts of other broad categories of security issues are provably impossible here, and we know that even though we didn't need to enumerate them. Instead, we focused on what the system should do instead of what it shouldn't do. So a little bit more about how we structure this in the different pieces of the system. At the center of it is a hardware instruction set that's interesting in its own right, called RISC-V. I don't know if any of you have bumped into this one. It's kind of an open alternative to the instruction sets pushed by Intel and ARM. So a nice property in an academic setting is you can implement your own processor for this instruction set, and no one will sue you for doing it. Really handy. So we created our own processor for one of the instruction set variations in this family. We formally proved that it meets the definition of the instruction set, which is like a mathematical formalization of the standards documents that you can find out there in English. Then on top of that, we have a programming language called Bedrock that we use to implement our code. In the software level, we have a compiler from that language to machine language, which itself has a formal proof of correctness. And then we can write the particular software, both application code and device driver code, and give each of those modules its own specification and proof, and combine that into proving that we meet that trace property that I talked about, formalizing the idea of light bulb is on only when it's supposed to be on. Another property that we got in this system, kind of, I think, mirroring important organizational aspects of deploying this stuff at scale in industry someday, is that we had different teams work on the hardware and software parts. And they could work independently because our new formally verified hardware could run conventional software, and our new formally verified software could run on an off-the-shelf microcontroller. And then after those projects had gone on independently, we had the integration experience of getting the theorems to talk to each other. That was still a fair amount of work, but we were able to get everything connected formally in the end. So then a really nice thing happens here. I foreshadowed this a bit earlier. We have all these layers of the system. Every layer in a typical system in the world today is an opportunity to make a mistake that breaks security or creates some other functional problem. Because we've done this end-to-end proof approach, we can view the system overall as a proved black box where we don't need to worry about mistakes in the middle parts that I've hidden with this rectangle. We have to audit the top and bottom level formal specs. We need to make sure we correctly wrote down what the application is expected to do, and in this case, what the behavior of a hardware design is. But we no longer need to trust or even audit anything that's hidden by this box. Like all the specific software and hardware isn't trusted because we've proved it. And all the specifications for those pieces aren't trusted either. Like the idea of the instruction set specification. If we made a mistake there, that endangers the top-level objective of this system, we would notice it in the course of proving the first system. So this is really a great protection against making mistakes, not just in this hardware and software artifacts, but also in the formal specifications that you need to write. And those are pretty complex bits of code in their own right, so it's really nice to have this protection. So what this kind of approach really enables, what I hope to see in the open source world and industry eventually, is someday you're going to visit GitHub and find there are a bunch of open source processors available, software libraries, compilers, hardware accelerators. You're going to pick your favorite, bring them together into a system. Each of these came with its own proof, which is also in GitHub, and you are able to recheck those proofs, not trust anything about the vendors who provided these pieces, and integrate those into your own new proof at the system level, which hopefully is significantly simpler, easier to put together than the individual components. And now you know you have a correct system. You can mix and match and swap in other open source pieces without having to go through some kind of audit about the code quality or trustworthiness of the source of that component that you received. That's really the future that we're hoping for here. And I'll just end with a quick plug for a startup company that I'm advising called Bedrock Systems, which is so far looking just at the software side of things, but they are building a hypervisor in the sense of, say, a replacement for what big cloud providers offer for running your bare metal looking code. And they are using these techniques to formally prove that the hypervisor gives you the appropriate security properties. And this is being aimed at, to start with, safety-critical domains like automotive and manufacturing, but with ambitions to a broader scope. And there's an interesting element here that this hypervisor also provides what's called active security. It is able to monitor the execution of code that you run on that hypervisor platform, detect evidence that something fishy is going on and we might want to stop that process. And that mechanism is itself being subjected to formal proof in this sense. And you can run your off-the-shelf software on this kind of platform. So it's a nice practical bridge from more of the clean slate approach that goes on in my lab at MIT to how we can get these ideas out there into industry. So ping me after the talk if you'd like to know more about this company or get connected to them. And I think now I'll finish a little early and just leave you with these links to the GitHub projects for the two case studies I highlighted. You can download these and recheck the proofs like I promised, or make changes and then see if you can adjust the proofs so that everything still goes through. And I hope that's kind of a preview of how maybe all of open source software will work 10 or 20 years down the line. Thank you. So I think I should start taking questions, and we have an overwhelming winner here, 21 votes. Any thoughts on how we shift security from being a cost center to a profit center? Yeah, this might be a digital technology and strategy question, which is not my usual realm at all, so I'm not sure I'm ready to address this. I've seen some of these words before, but I'm not used to saying them. Let's see. I think at least being able to have a clear, objective sense of progress in security would probably help in terms of, let's say, being able to give some sort of metrics about this fraction of our code base now has this really strong mathematical element of security that's been checked for it. And this is probably hard to do with conventional approaches where you just pile on different security products from different companies and they're all claiming to check important properties, but you don't really know how much progress you've made. So perhaps the kind of tools and approaches that I'm arguing for here will be a bridge towards being able to help management see quantitative progress towards a more secure code base company-wide, and that can help this start to feel like a profit center. I'm ready for the next question. Okay. I'll take the top left one. What's your view on the impact of quantum computing on security? Wouldn't it make the arms race worse? Well, probably the element of quantum computing that I'm most aware of from a security perspective is using quantum computers to break cryptographic schemes. And there's a lot of work going on in the cryptographic community now about so-called post-quantum cryptographic algorithms. I I don't know exactly what stage it's at now, but there's a NIST, National Institute of Standards and Technology competition to develop the standardized post-quantum cryptographic algorithms of the future. As these things go, in the cryptographic world, there was a list of finalists in that competition, and quite a few of them have been hacked and broken since then. But I think there are roughly 2 left standing at this point. So we have experts looking into that. So at least from the cryptography standpoint, I think we're going to get standards of how you do cryptography to be ready for the coming of quantum computers. And once that's clear, I think the kind of technology I presented here will be a great candidate to use to develop and certify the implementations of those cryptographic schemes. Quantum computing also matters on the other side. We can implement cryptography or other security-relevant functionality using quantum computers. And yeah, presumably the attackers already have some great ideas of what they do with quantum computers that haven't occurred to the defenders. Does it make the arms race worse, though? I don't know, kind of sounds like business as usual to me, not obviously that different from other new technologies that have arisen. Next question, practically speaking, aren't there too many vulnerabilities or new capabilities being developed by hackers to definitively prove a system to be secure into perpetuity? Yeah, that's an important question, which I tried to get at a bit in talking about how by focusing on proving not what a system shouldn't do, but instead what it does, and in a way where you know it doesn't do anything else, you can get around some of the apparent challenges of there being so many ways things can go wrong with security that you have to enumerate all of them and check, can this happen, can this happen, can this happen? For instance, in our example of the IoT light bulb system, where we proved all this system does is it turns the light bulb on and off according to these rules about what network packets are allowed to trigger what state changes. We did not need to make a list of all the problems we're worried about, like buffer overflows and code injection vulnerabilities and integer overflows and all these other low-level software issues. We do need to worry about whole new categories of system behavior, like if we weren't thinking about information leaks through the timing of a system, didn't put anything about timing in the system we're proving, then we could really be caught off guard. Then we would go back and decide from now on, all the system-level theorems we prove had better include characterizations of timing and how secrets are not leaked through the timing of the system. So the hope is these whole new categories of behavior, maybe every 5 years there will be one big one that pops up, and we hope this is a relatively feasible engineering undertaking for the whole community to then start taking those into account in the formal certifications that they do. But it shouldn't be a question of watching the vulnerability lists week to week and having to constantly adapt to new ones by changing your theorems. Who provides funding for this type of work, and what is the cadence of that funding? So there are a number of federal agencies in the US that are really into formal verification these days. DARPA has been a big supporter. And IARPA, the intelligence equivalent. The National Science Foundation supports a lot of work in this area. I was part of a big NSF expedition. That's the name for the largest computer science grants they give on precisely this topic of whole system proofs across layers that span hardware and software. And companies are increasingly interested. Within the broader area of formal methods, at least, Amazon has a lot of activity going on. I think they might have hundreds of people working on this sort of thing now. We've had a lot of success working on technology transfer with Google, and they provided some funding for this work. There were people doing some related things at Facebook. So I think and Microsoft is really a long-standing center of this kind of work, starting in their research labs and moving out into products. So at least among the biggest tech companies, there's a fair amount of investment in this kind of stuff. And I think we're at the stage of maybe seeing these ideas make a jump to the next tier down of size of companies and hopefully become a standard part of software development in the next 10 years or so. In this approach, is this approach an option when source code is not available, such as when an application is purchased from a vendor? Yeah, that's a hard one. I personally only work on open source systems, whether they're software or hardware. I think there are research challenges in proof obfuscation, where you could demonstrate that, say, a piece of machine code that you've given to a customer meets a specification without giving them too much insight into the implementation details of that component. I'm not aware of concrete projects in that style, but on the other hand, in my research project, it's pretty hard for me to read the proofs my students are writing, so maybe those don't give away too much in the first place. And so at least at first, there's kind of a security by obscurity element here where there aren't many people yet who are trained in these formal methods tools, so they won't know what to do with a proof that at some level might be revealing details of how your system is implemented. And then in the longer term, I think this is an important, interesting research area of how to generate this kind of evidence without revealing too much about the way your system is architected. What about scale? How realistic is it to prove there are no vulnerabilities in software systems with millions and billions of lines of code? Yeah, I guess one optimistic answer, which I'm sure will strike many people as naive, is as our programming tools and frameworks and approaches get better, maybe we won't have billions of lines of code systems in the future. At least I'd like to live in that future. But also there are a lot of scaling challenges here. That's most of what my group does is dealing with scaling challenges. For instance, this is all about writing proofs at a very minute level of detail. You really aren't allowed to take anything for granted in creating a logical argument that should be convincing to others via automatic proof checking. So we spend a lot of time on proof automation, tools that automatically write proofs within specific domains for us. So we don't need to trust those tools because they generate arguments at a lower level of explanation. But they can really accelerate the productivity of the engineers who are developing these systems and arguments. Are there considerations with possible random hardware failures that can impact proved systems? Definitely. This is one that has gotten relatively little attention in the formal methods world, but there are definitely people thinking about how do you know that intermittently failing systems are correct. In principle, if you know enough about the failure model of your hardware, where you can write down a probability distribution of how frequently it's going to fail in different ways, you should be able to prove a probabilistic theorem bounding the chance that particular bad things happen. And we certainly have all the math on paper for explaining that kind of argument, and I think the community is increasingly looking at how to make that all rigorous enough to fit into this kind of framework. Don't you need to prove the compiler itself to thoroughly trust the code you have proved? Definitely. A large fraction of the work in my group is proving compilers. This turns out to be a case where at least it's relatively clear what the right theorem is. You want to say, compiler produced some code that has the same behavior as the code that went in, but there are all sorts of gnarly details inside the compiler, say associated with optimizations that make it non-trivial to show this property. Nonetheless, this is one of the most mature areas of this tradition of formal methods, and there's a lot of work that proves compilers. What about vulnerabilities in the specification or in the proof systems? Yeah, so I did mention one sense in which we can avoid getting caught by vulnerabilities in the specifications, which is in a layered system design, create an end-to-end proof, and then the specifications in the middle are no longer chances for you to make fatal mistakes. Because if you got one of those specifications wrong, it will have to manifest somehow in some issue proving the larger system theorem. Still, you have specifications at the top and the bottom that you need to indeed read very carefully. And then there are the proof tools themselves, which are opportunities for bugs to trick you into thinking you have a secure system when you don't. And I like to think the way we should go about that eventually is MIT and other universities should offer classes that large fractions of the computer science majors take, where they have to audit these tools and they can get academic credit for finding bugs in them. We just want to get a lot of eyes on these systems. And this is an improvement over ad hoc security auditing today because we hope there's a relatively small set of really security critical software, the proof checking software, and we just want to get a lot of eyes on that. And then all these other systems that are certified using that software benefit from that exercise, as opposed to having to have their own ad hoc audits today. In layman's terms, we are trying to constrain our case with boundary conditions focusing on intended functions to limit what we need to defend against for each case or application. Let's see. I suppose that's right. We want to have as simple an interface as possible by which the full system interacts with the world so we can characterize completely what are legit interactions, and we will therefore naturally not describe bad interactions like a funky packet arrives and the system is now part of a botnet. And by limiting the interface, we make it more feasible to give a complete description of what interactions with the world the system is allowed to have. And then we have this nice security payoff of ruling out all kinds of gnarly scenarios that we did not need to enumerate. And I think that's probably the last question. So thank you very much.